Hi everyone, so this is the third video in the alkene series. In this video, we're going to be talking about hydrations of an alkene and hydroxyalkoxylations. And so for this first reaction, we're looking at the hydration of an alkene. In this one, we're adding a water molecule across a double bond. And so in our reagents, we always have that alkene or double bond, and then we have water and then some source of acid. And so most commonly that's H2SO4, but sometimes it's also H3PO4. And then occasionally you might also see that you don't have both reagents and your instructor might just write H3O plus directly. And H3O plus just indicates that it's water in the presence of an acid. And so it will also fall under this class of reactions. And what we'll see is that whenever we react these reagents, what we end up doing is adding a hydrogen and an OH across that double bond. And so we'll see that that double bond goes away and becomes a single bond. And then we added an OH and H here. And so now we can talk about the mechanism. In the first part of this reaction, we form that H3O plus. If you already had H3O plus, you can skip this step. It wouldn't be necessary to draw this out. Basically what we have is H2O, and then we have our reagent sulfuric acid, and I'll draw out the structure of H2SO4 like that. And so what we have is that the oxygen electrons pick up that hydrogen and form H3O plus, and then plus our conjugate base. All right, so now we have our H3O plus, which we can react with the actual starting reagent. And so for this, I'll just copy the one that we have up there. So we have our double bond. And this is very similar to what we had in the previous video, where we have that the double bond attacks the hydrogen in the H3O plus. And that's our acid instead of HI or HBr or HCl. And so in this reaction, it's always easier to draw out H3O plus like this, where you show those electrons between the H and the O, so that you can just directly pick up that hydrogen, give those electrons to the oxygen. And in doing so, we end up adding that hydrogen. And if we recall from the previous video, we want to put the carbocation in the more stable position, which is going to be that tertiary position. And then we also reform water in this step. In the next step, we want to look for rearrangements. And again, we're looking for either secondary to tertiary or secondary to secondary with resonance. And in this one, we already add a tertiary position, and there's no rearrangements that are possible. And so for our reaction here, we'll have no rearrangements. However, I'll do a practice problem at the end of this video where we do look at rearrangements. All right, so next we can take our carbocation. And so now we have that carbocation is electrophilic because it wants electrons, it's positive, and it can get those electrons from another water molecule where those electrons from the oxygen can attack here. And so now we form this intermediate. And so what we want to know is that those hydrogens right here, they didn't go anywhere yet. We still have OH2 that added on. And so we have a positive charge on this oxygen here. And so we have our last step here that has to deprotonate that OH2 to form OH. And so we'll redraw that OH2, and I'll show those, I'll redraw that OH to show those kind of, those electrons that are in that bond. And then we'll use H2O to do a proton transfer. And note that I'm using H2O and not OH minus. If we recall from the reaction conditions, we're in acidic conditions. And so at no point should we have a negative charge anywhere in our reaction. And so the base that's going to deprotonate the hydrogen here is going to be just another regular water molecule and not OH minus. And so here we formed our final product that I just boxed in red. And if we look up here, we can see that it matches this one that we had up here. All right, next we can do one with a rearrangement. And so we're going to follow the exact same steps. I'm just going to kind of write it out more cohesively here. And we're also going to be on the lookout for a rearrangement. And so same thing as before, our first step, we're going to form H3O plus. So we'll have, I'll just use shorthand to describe H2SO4 here. So we have that, and so we formed H3O plus. And so that's going to be our step one. Next, we're going to have that alkene attack that hydrogen. And so for this, I'm just going to redraw it down here just so we're off space. And again, I'm going to redraw the H3O plus as HOH2 plus so that we can more easily show this step here. And so now we formed a carbocation here and added that hydrogen to the terminal carbon. And so technically it's right here, but I'm just not going to draw it in because it'll just be a little bit more easy to look at the compound like this. All right, so now we're at a secondary carbocation, and so we want to look for potential rearrangement. And so what we see here is that we actually have a dashed hydrogen right here that can undergo a hydride shift here. And so we can get a 1,2 hydride shift to shift over that carbocation to that middle position here and the hydrogen to the other one. And for this one, make sure that you draw this methyl group in plane and not wedged. Even though it was wedged right here, in this structure here, we don't actually have wedged and dashed geometry because we're trigonal planar. We only have 3 groups there. And so we want to draw that group in plane. All right, next we have the water molecule come in, OH2 comes in. And so we end up getting OH2 plus here. And I'm not showing any stereochemistry here. We have, technically we have the same molecule regardless of whether they're wedged and dashed because they both have ethyl groups. But again, whenever we proceed through a carbocation intermediate, we never want to show stereochemistry because it can either be wedged or it could be dashed. All right, and then in the last step, we want to deprotonate. And again, we'll just use water for that. Or some classes like to use that HSO4 minus that was formed in that first step, but we'll use water here. Okay. And so we have that the oxygen picks up a hydrogen, and then the electrons between the oxygen and the hydrogen go to the oxygen. And so now we'll end up getting an OH here. And this will be our major product. All right. Okay. All right. So the next set of reaction, or the next reaction that we're going to do is hydroalkoxylation. This one's very similar, except instead of H2O, we're using some sort of other alcohol. And so for alcohols, or for water, we have HOH. For alcohols, we have some R group and then an OH. And so this reaction is going to be identical, except instead of having a hydrogen, we're just going to have an R group. But all the steps are going to be the same. And so in this one, instead of adding an H in an OH, what we're adding is an H and an OR group. And our R in this case is going to be that methanol. And so I'll substitute out that R for that methanol or methyl group. All right, so same exact mechanism. We're going to, in our first step, form, let's say H2SO4. We're going to form our ROH2 group. So here we have MEOH was our starting group. So I'll just draw that here. Same thing. We're going to pick up that hydrogen from the H2SO4 and form OH2 positive with that methyl group plus the conjugate base. Next, we have that nucleophile-electrophile reaction between the alkene and our OH2 group, or source of acid. And for this one, I'm going to draw this as the H so that we can see what happens to that H when the alkene attacks the hydrogen and gives its electrons back to the methanol. And now we end up forming that carbocation. And similar to that last question, we're going to form that carbocation in a more stable position there. Next, we want to check for rearrangements. And since we're working with the exact same starting, we're not going to get any rearrangement similar to that first question that we did. Next, same as before, instead of the water, we now have that ROH group attacking that carbocation. And so now we have this methanol, electrons from the oxygen coming in and attacking there. And so this will be our nucleophile, and the carbocation is our electrophile here. All right, so last we can draw out this, and here we have that similar to that OH2 group in that previous question, we have a positive charge on the oxygen. And so our last part of the mechanism is going to be to deprotonate using another methanol. And again, we never want to use the deprotonated one here because we're in acidic conditions, we don't have any base around or negatively charged base around. And so our final product will look like this, or if you prefer using ME, you could also write your answer as OME here. Either one is it's the same thing because this methanol just represents this methyl group right here. All right, so that's that. We can do one with a rearrangement here. It's a little bit different from that other molecule that we did in the previous question. So step one, we're going to form our protonated alcohol. So I'll redraw our alcohol, and so we can tell it's an alcohol because it has this OH group and then the R chain. And so we'll protonate here and form OH2 positive here. Next, we can take our starting molecule and react it with that one, where we pick up a hydrogen and protonate that alkene. And so here we're going to put that carbocation on that secondary position, and that hydrogen goes to the outside. And so here we can look for rearrangements. And so since we're secondary, we potentially could form a resonance stabilized carbocation at this other position here. And so what we can do here is shift over one of these hydrogens through a hydride shift to form a resonance stabilized carbocation. So we have one hydrogen there left and a carbocation that is resonance stabilized. Disappeared for a second. Okay. Next, what we want to do is take that resonance stabilized carbocation, and now we can react it with our starting alcohol. And so I'll redraw that alcohol here. And we have the electrons from the oxygen coming in and attacking there. And so it's going to look a little bit wonky because it's pretty big. But we end up having this reagent here. And I'll shift this down so we can more easily see what's going on. And we have a positive charge on that oxygen. Finally, in the last step, we have another alcohol come in and deprotonate that hydrogen. And so our final product is going to look like this. All right, so that gives us the product to this reaction. If you haven't done so already, I recommend checking out the alkenes practice problems video, link below.